All right, so let's take stock of where we are. We've shown that if you have a system of equations, you can find an equivalent augmented matrix. Whoops, not ag matrix, but aug matrix, that contains the same information as that system of equations. We've shown that any augmented matrix can be reduced to reduced row echelon form. Right. Well, now we want to characterize the possible types of solution sets for a system of equations. And what we're going to do is we're going to characterize that by looking at the reduced row echelon form. Because we can not only go this way, but we can go backwards. We know that every augmented matrix has a unique reduced row echelon form, and every system of equations has a unique augmented matrix. So if we characterize the solution set corresponding to this reduced row echelon form, we've characterized the solution set for the system of equations. In other words, we can forget about all this complication. All we have to look at is the solution sets for equations corresponding to matrices in reduced row echelon form. Now, we've seen examples where we have systems of equations that have no solutions whatsoever. So there's an important division between systems of equations that have solutions and systems of equations that don't have solutions. That's the distinction made in this section when we talk about consistent systems. A system of linear equations is consistent if it has at least one solution. Otherwise, it's inconsistent. Now, notice this at least. It could have more than one. All right, we'll leave that for later. All right, so we'll want to figure out or characterize when the system is inconsistent or consistent. And as I said, we'll do this by analyzing the reduced row echelon form of the matrix. In particular, we're going to look at the columns D and F. D, if you remember, were the pivot columns, the columns that had a leading one in the row, and F were the other columns. Okay. All right, so let's look at some examples. Here we have a reduced row echelon matrix, and we know that this is associated with a system of equations. You remember how to do that? This first column is variable x1, second one is x2, third one is x3, x4, x5, x6, x7, x8, and then this is the constant column. Right? Now, if we think about the pivot columns, we have a pivot column here, pivot column here, a pivot column here, and a pivot column here. Those are the D columns. So I could say D is equal to the columns 1, 3, 4, 5, and 7. Now F are all the other columns. So F are the columns 2, 5, 6, 8, and 9. Okay? Now, the quantity R is the number of pivot columns, and it's also equal to the number of non-zero rows. You can see that every non-zero row is going to have a first element, and every first element is going to correspond to the number of pivot columns. So R is equal to the number of non-zero rows, and it's equal to the number of pivot columns. Okay? So here we go. Notice that the set D and the set F together make up all the columns. Now, this number R, which is the size of D, another way to write this is R is equal to absolute D. That means R is the size of D. This number R tells us a lot. As I mentioned before, it's the number of non-zero rows, and it's also the number of pivot columns. All right, now, before looking in general, let's see how these things work, how R and the reduced row echelon structure of the matrix determine the nature of the solution set. All right, so let's try this system of equations. It looks rather complicated, but we're going to let the book do the hard work for us. First thing, of course, is we want to change this into an augmented matrix, and I'll leave that to you. Of course, you need to be careful about the gaps. Here there's a 0x3 here. Remember that you have to associate these coefficients in columns. This is the x1 column, the x2 column, x3 column, x4, x5, x6, x7, and the constant column. Constant column gives us the column on the other side. Now, it turns out that if you write this augmented matrix and then you find its reduced row echelon form, you end up with this. I'm not going to go through that because when you have a system this large, you never do it by hand. You'll always use the computer. All right, so you'll just take my word for it that when you take this system of equations and find its reduced row echelon form, you'll end up with this form here. Now, what are our sets? D is the number of D is the pivot columns, and we see we have a pivot column at 1, 3, and 4. And all the other columns are non-pivot columns in the set F. So naturally, R is equal to 3. Here's some notation that's useful in the proofs. We see here that x1, x3, and x4 are associated with D. So 1 was the first element of D, so we call it D1. 3 was the second element, we call it D2. 4 was the third element, D3. So we would say x1 is xD1, x2 is xD2, x3 is xD3. I'm sorry, let me say that again. x1 is xD1, x3 is xD2 because 3 is the second index in D. And x4 is xD3. So we're using this index DI to denote which place it is in this set D. Similarly, we can talk about the x's in the set F. F1 is x2, xF2 is x5, and so on. All right, so let's see how we work on getting a solution here. Once you have an equation like this, remember what this really means, this first equation is x1 plus 4x2 plus 2x5 plus x6 minus 3x7 equals 4. Now, you could take all of these variables and put them on the other side. Right? That would give me x1 equals 4 minus 4x2 minus 2x5 minus 1x6 plus 3x7. And if we do that, we get the pivot variable x1 in terms of all the other variables. Okay. We can do the same thing for x3. If I move all of these variables to the other side, that's saying same thing as saying x3 equals minus x5 plus 3x6 minus 5x7. Now that's exactly what we have here. Last equation here, if I move the other variables here to the other side of the equation, that tells me x4 equals minus 2x5 plus 6x6 minus 6x7. That gives this here. Now, notice that these variables here are all pivot variables. And notice that these variables here are all free variables. They're all variables that correspond to this set F, right? x2 corresponds to this index 2. x5 corresponds to the 5, etc., etc., etc. So what have we done? We've expressed the pivot variables in terms of the free variables. Now he notices that another way of calling pivot variables are dependent variables, and another way of talking about free variables are independent variables. So the values of these pivot variables depend on the values of the free variables. Now, free variable seems to imply that I can choose these values however I want. And in fact, that's true. No matter what x2, x5, x6, x7, and x7 that I choose, I will get a solution to this system. Why is that? Because the only conditions on these variables are expressed in these equations. So as long as I can arrange x1, x3, x4 to satisfy these equations, I'm good. The free variables are indeed free. I can choose them to be anything I want. Well, of course, they have to be real numbers, but that's the only restriction. Now, how can we write this solution? x5, x2, x5, x6, x7 are free. They can be anything. So in my solution set, I let x2, x5, x6, a7 remain as variables. x1, x3, and x4 are determined. They're dependent upon x2, x5, x6, x7. So I need to express them exactly as this equation. So this set here gives me all possible solutions. Now notice he's allowing for complex solutions. Typically in our class we'll talk about real solutions, but the principle is the same. Okay. Now, hopefully you can see that you can do this same approach with any reduced row echelon form. There is nothing special about this form. Whatever I did with this form, I could do with any reduced row echelon form. Okay. Let's try another one. Let's look at this example. All right. So here we have another case of variables. And we can change this into an augmented matrix and take my word for it that this augmented matrix corresponding to this system reduces to this reduced row echelon form. So here we have the pivot columns, again 1, 3, 4. And the free columns are 2, 5, 6. So this is correct. D is 1, 3, 4 and F is 2, 5, 6. R is equal to 3 because there's 3 elements of D. Right. Now I can do the very same thing. I can write this first row as an equation where the dependent variable is expressed in terms of the free variables. Right? Again, we have x1, x2, x3, x4, x5, and the constant. So this first equation would be x1 equals 6 plus x2 minus 3, what is that? x5. All right, that's what we have here. This is correct. The second row here, if I change it into a equation, this pivot variable corresponds to x3, so I'm going to get x3 equals 1, and then here I'm going to have plus 2x5. When I take it to the other side, the sign changes. So this gives me, because my second row, and you can see that the third equation, x4 equals 9 minus 4x5. This is correct. So I can express my solution again in terms of the free variable. Here now we have 2 free variables, x2 and x5. And my x1, x3, and x4 can be expressed in terms of those 2 free variables. All right. All right, now in both of these cases, we've seen that there are solutions. In fact, both of these cases have had infinitely many solutions, not just a single solution. Right now, we're not concerned about the number of solutions, but simply whether or not there are solutions. And there's a way of showing easily when there are solutions to a system of equations. If you have the reduced row echelon form, you can use this fact to determine immediately whether or not this corresponding system of equations has solutions. Let's read this carefully. Suppose A is an augmented matrix of a system of linear equations with n variables. Now, if it has n variables, then it's going to have n plus 1 columns, right? Because the last column is the constant column. All right, now, suppose also that B is a row equivalent matrix in reduced row echelon form with R non-zero rows. Okay. Then the system of equation is inconsistent if and only if column n plus 1 of B is a pivot column. All right? So what is this saying? This is saying that all you have to do to tell whether a system is consistent or not is look at the last column. If I have a matrix, here, let me pull up my whiteboard here. If I have a matrix here, reduced row echelon matrix here, so I'm going to have ones, and then I'll have non-zero entries or something. Then I may have another one and more non-zero entries here. And of course, you'll have zeros here above and below. You'll have zeros here, and zeros here, and so on. Now, if I look at the last column, if there's a 1 in the last column, then there's no solution. Now, you might wonder what's going on here. Why is that the case? Well, think about changing this system back into a set of equations. The first column corresponds to variable x1, second column corresponds to variable x2. The last column here is going to be xn, then this is the constant column here. What equation does this last row correspond to? Well, you have 0 times x1 plus 0 times x2, blah, 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 0 times xn equal 1. In fact, that last equation is 0 equals 1. That doesn't work. Okay, so this system in reduced echelon form, if there's a 1 in the last column, if there's a pivot in the last column, it includes the equation 0 equals 1, which is impossible. On the other hand, if there's no 1 in the last column, if there's no 1 in the last column, then we can use the procedure that we've been seeing to always get a solution. We can always take every one of these pivot variables and express it in terms of the free variables. Okay, so really there's your if and only if right there. If there's a 1 in the last column, there's no way that system of equations has a solution. If there's not a 1 in the last column, I can go ahead and find a solution by constructing, by using the same method that we've seen. Now, the informal discussion that I just gave corresponds to the proof that he gives here. What does this mean? This means he's first proving that if column n plus 1 is a pivot column, then the equations are inconsistent. And here he says that if the n plus 1 column is a pivot column, then that corresponds to the equation 0 equals 1. Now he's trying to prove the other way, which is to say, if the systems of equations is inconsistent, then column n plus 1 is a pivot column. We can prove that by proving the contrapositive. The contrapositive states that if column n plus 1 is not a pivot column, then the system of equations is consistent, and that's what we can show just by our procedure. All right? So we've resolved the question of when a system of equations is consistent. The second question we want to address is, when does a system of equations have more than one solution? We've seen cases where it has one solution, and we've seen cases where it has more than one solution. Now, if you look at these cases that we did here, these examples, this had more than one solution, and this example also had more than one solution. Why is that? Because I could choose any value of these free variables. So in fact, this has infinitely many solutions, and this has infinitely many solutions as well. What we see in these examples is in fact true in general. Whenever you have a free variable, you'll have infinitely many solutions. And the reason is, just as I said in the discussion, the free variable can take any value. Now, what if the system has no free variables? Well, if it's consistent, then it has a solution, but if there are no free variables, there's nothing arbitrary, and the system has exactly one solution. So now we have a complete characterization of the types of solutions. We know that if the system is inconsistent, the last column is the pivot column, and now we can show when the system will have infinitely many solutions or not. Read this theorem carefully. Suppose A is the augmented matrix of a consistent system. So we're assuming at this point that we already know that it has at least one solution. Suppose A is row equivalent to a matrix in reduced row echelon form, and suppose it has R pivot columns. Right? Then in order to be consistent, R must be less than or equal to n, because n plus 1 is not a pivot column. Now, if all the columns except for the last column are pivot columns, then there are no free variables. That means the system has a unique solution. But if the number of pivot columns is less than n, then there's a free variable, and the system has infinitely many solutions. All right? Now, this proof basically expresses what I just said. You can read it through and see that it corresponds to exactly what I said. All right.